Okay, good morning everyone and welcome back to the second lecture today. It's my pleasure to welcome Professor Alicia Sintes as a speaker for the second course this week. Professor Sintes is coming to us from the University of Balearic Islands in Spain. She started her career with a PhD at the same university, incidentally, before moving on to the Max Planck Institute for Gravitational Waves for a postdoctoral tenure. Professor Sintes' work focuses on various aspects of gravitational wave astronomy, especially on continuous waves and their searches and so on. She's the senior researcher of gravitational physics at UIB. She's a member of the LIGO Council, the GEO Executive Committee, the LISA Consortium, and the Einstein Telescope Science Team. She has also been an advisor to the European Space Agency and is a member of the board of the Spanish Society for Gravitation. She has received numerous awards for her foundational work, and this week she'll tell us a lot about the searches and detection methods for continuous waves with like ground waves detectors. So, Professor Sintes, please take it away.
Thanks a lot for the introduction, and thanks a lot for inviting me to this fantastic place here, ICTS. For me, it's a pleasure to be here. This is my second time in India, but it's the first time at ICTS. And I'm looking forward to really to come back because this is a fantastic location. And I hope that you are enjoying the lectures of these 2 weeks. So yes, this course is going to be about methods and results to search for continuous gravitational waves. But before I start talking about methods, I will have to explain you a few things about some very basic things. I will have to explain you things about the signals, about the noise, about the statistics, and then that we will continue. So with that, I will start already my first lecture, that is quite basics, and I will start with the signal. To start with the signal, let me go back to Einstein field equations. So if we go back to the Einstein's equations, that you might know. Now we could be considering the case of the very weak field. In the weak field, we can approximate the metric tensor by Minkowski plus some perturbation. Well, this perturbation is very small. And then we can continue doing further things. So with just these things, we can write the linearized Einstein equations in the following way. And I think I have already been losing some of the constant factors because I might already start doing G equals C equals 1, I already see. And here I have already made the approximation that we have been using the Lorentz gauge of harmonic gauge, in which, in this case, in the Lorentz gauge, x mu nu is equals 0, or equivalently, G mu nu gamma equals 0. And by introducing the transverse traceless metric, then we get that the linearized Einstein equation basically gets simplified and written much simpler, like h mu nu equals minus 16 by t mu nu, and then I have to add the gauge conditions. So from here, I can make assumption that I'm in vacuum, and in the case of vacuum, basically, I have this equation just simply becomes this. And the first solutions that we can get from here are plane waves in which the wave equation is going to appear to be null. These waves are also going to be transverse. And finally, this can be written as 0, 0, 0, 0, 0, C11, C12, 0, 0, C12, because it's symmetric, it's trace-free, or basically in this TP gauge, we just get that this can be written in this way. Another part of information that we might want to consider is coming from the geodesic deviation equation. Here we can try to deduce what will be the effect of these perturbations, of these gravitational waves onto matter. So if we are considering free test particles, we might not see the thing, but if we consider the distance between two free test particles, and if I consider and these particles basically in the limit of very slow motion, if I consider the distance between these two test particles, if I call it S, one can easily deduce that for very slow moving particles, coming from this geodesic equation, this can be converted into a very simple equation in which now even the proper time and coordinate time are assumed to be the same. From here, then you can see what is the effect of gravitational waves into matter or as they travel. And basically, from here one can see also, if we consider, well, if one considers, let's say, a ring of free test particles, then just trying to solve this equation for the two different polarizations, one can see that for the plus polarization, basically this ring that gets the form in this way, and for the cross polarization, a ring of test particles basically will get the form in this way. So that gives the idea that basically how we can construct gravitational wave detectors. The initial detectors were basically resonant bars, and the modern detectors that we will be talking and presenting the results are interferometric detectors that they have an L shape, and basically if we will have signal traveling on top of this detector, well, or basically in any direction, what is happening is that is going to change this distance of these arms. Okay, so given said that, in the long way approximation, in which the length of the arms is much, much smaller than of the signal, basically the strain of the gravitational waves at the detector basically can be measured like the difference of the arms, that is a function of time, divided by this. So if this detector, I'm thinking of an interferometric detectors, and I have two arms, and this N1 and N2 are the unitary vectors along the two arms, then this response of the detector can be measured in this way. Where this N1 and N2 are these unitary vectors along the arms, and H is going to be the three-dimensional tensor of the perturbation. So here this H is the 3D perturbation tensor at the detector. The perturbation tensor of the source is what I've just described some minutes ago. So my perturbation tensor in the source frame is just going to be this H plus H cross 0, H cross minus H plus 0, 0, 0, 0. But now what I have to do is to transform this perturbation tensor from the source frame into the detector frame. So basically I have to convert from coordinates in the neutron star frame into coordinates in the detector frame. So I'm quite bad with drawings. So but basically, if here I have my 10 neutron star, here there is the Earth, and I have my detector, then this is going to be all this, or in the other direction, the third component. What we have is that in order to convert this perturbation tensor from here to here, basically this is just going to be a simple multiplications of rotation matrices. So this is going to be the exercise that is going to be given to you to actually to compute all these things. So basically from here, there is a first angle that is going to be a polarization angle. So it's going to imply that the first rotation you will have to do is going to be a rotation with respect to the z of a certain polarization angle. But then you will have still the x, y, z here rotated with respect to the x of y, z here. So the next rotation you do is with respect to the y angle. Try to put the two z parallel. And if this is in a scale location characterized by phi n and theta n, the next rotation one has to do is minus theta n plus pi. And when this rotation is done, the last one that one has to do is to again rotate with respect to the z angle minus phi n, so that all they are in parallel. The unitary vectors n1 and n2, one could take it in a very easy case in which n1 just could be 1, 0, 0, and n2, 0, 1, 0. Or we could even make it more complicated. Let's say for space missions like LISA, or for future detectors in principle like ET, that in which the arms are not separated or 90 degrees, but they have different angles. And if they have different angles, one could write n1 as cosinus
Ma'am,
Yes?
is it possible for you to write in a bigger font?
Bigger font?
Yeah.
Yes, I will. I'll finish this equation small and then I'll try to write it bigger. Thank you. Apologize for that. So basically, given a separation angle of whatever letter you prefer, then this n1 can be the cosinus of pi 4 minus this angle divided by 2, then the sinus of the same quantity and 0, and this is the sinus of the same quantity, cosinus and 0. So that basically when this is 90 degrees or pi halves, then these two become 1, 0, 0 and 0, 1, 0. If you do that, and then either you can use a certain angle or not a certain angle, this quantity here, basically, it gets converted that the strain depends on time, depends on the sky location of the source in the sky, depends on the polarization, etc. And this can be written as a linear combination of the two polarizations and these two functions, f plus and f plus and f cross, are the response function of the detectors or the detector's antenna pattern. Then what are the values of these functions? It's going to be something that you will have to compute, and I can warn you that there is some interest depending on what reference you take from the literature, because there are going to be a number of conventions on how things get measured. Like if the n angle was from the source to the detector or from the detector to the source, then you will have a number of signs that can get changed. So this is 1/2 of 1 plus cosine squared theta cos 2 phi cos 2 psi minus. So this, well, I can just point you which, well, all the signs. And these are going to be your two expressions that you will have to compute. How you will get to compute, basically I just explained you here, but basically you have to convert this 2 that it was in the source frame into the detector frame, and basically how you get it is via this transformation where this M is going to be the matrix to change the basis, is, as I just said before, are these quantities here. The same two expressions that you will see, in continuous waves, we like to write them slightly different. So we like to write them, yes, they are time dependent, they are sky dependent, and polarization dependent. We like to introduce functions A's and B's. And in the case of continuous waves, we have that the two polarizations can be written as an amplitude term with a cosinus here, and the other one, the other amplitude where the frequency say in the solar system barycenter frame will be written this way. If I'm talking about continuous gravitational waves, let's say I've already created neutron star, not a just born neutron star, then basically there is going to be a very slow varying of this frequency. So I'm assuming that the intrinsic frequency varies very slow, then I can just simply expand this function around a certain reference time. So if I do that, I can write the phase as a certain initial phase, and then simply a Taylor expansion summing around number of spin down parameters in which, of course, any of them at a certain reference time is just the derivative, the S derivative, evaluated at this reference time. Tau. Tau and? Don't understand. Here is tau, and here I've written T. I'll come now. Because this should be the time at the detector frame, while this slow varying function of time is true, let's say, in the neutron star reference frame, or almost the same in the solar system barycenter. Now, I have the source, I have the sun, and here I have the Earth. Of course, the Earth rotates and moves, so the wavefront is not arriving at the same time at the solar system barycenter or at the Earth. So there is a relation which is, for example, this quantity that appears here, that is delta tau at a given time and for a certain sky location, it will be tau minus time reference, and the relation between the time solar system barycenter or the time at the detector can be written like T R times N divided by C. And here I should be doing a better drawing. So if I have my source, with a certain N, that's the solar system barycenter, and here I have my detector. This is the position of the detector from the solar system barycenter, and that's the location of the source in the sky. So this is the timing relation between the waveform arrival time at the detector frame and at the solar system barycenter. This is quite important because, as I said, we like to simplify those expressions in writing these A's and B's. But also we like to separate what we call amplitude parameters from Doppler parameters. And in particular in continuous waves, we like to write that this quantity here can be written as a sum of 4 terms of some amplitude on waveforms, in which this is what we call the Doppler parameters. In particular, these expressions, H1 is A of t, cosinus phi of t, H2 is P of t, sinus phi of t, H3 is the A with the sinus, and H4 is this, and the A's are A plus cos phi 0 cos 2 phi minus A cross sinus phi 0. These expressions that are kind of lengthy, in any of the references that I've given to you, you can find them, or these were originally derived in the Yaranowski-Kralanoy-Schutz paper. And this is basically then the basis of something that is going to be called F statistics that I'm going to describe in the class tomorrow. As you can see, these A's, A1 to A4, are only depending on these 4 parameters, A plus, A cross, the initial phase, and the polarization phase, while the rest of the parameters, what we call the Doppler parameters, are included in the H1s. This is the I plus. The main reason is that there are a lot of difference in the dependencies. So basically, for many searches, we will have to, or for all the sky searches, we will have to explicitly search for all the Doppler parameters that will be sky location, frequencies, and frequency derivatives, while we don't necessarily need to search for all the other parameters. In some cases, you can maximize them analytically, and then you will get it for free. So now I want to talk a bit more about the signal, and I'm just going to give you some expressions that will be explained much better in Professor Ryle's talk. It's like, okay, what are the expressions of this A plus and A cross? So I can make an assumption. So my first assumption is going to be that I'm going to talk about the case of a triaxial neutron star. And for this case, H plus is 1/2 H0 1 plus cos iota squared, and the H cross is H0 cos iota. What is this other angle here? Is that if I have my neutron star. This is its rotation angle. And here is the Earth. Basically, I'm having two things, two parameters that have appeared here. H0, that is the wave amplitude. And in this case, the wave amplitude is characterized by 4 pi squared g c to the 4th epsilon z distance f gravitational wave squared, where, well, this is g, then this is the triaxial ellipticity that is going to be introduced as well. That is basically the differences of this moment of inertia. So this is like the mountain case that Keith has described, that is not necessarily need to be a mountain. D is the distance. I by z is this principal moment of inertia. This is the frequency of the gravitational waves. And in this case, the frequency of the gravitational waves is going to be twice the rotational frequency. And yacht is the inclination angle. And this basically is the inclination angle from the side. Oh, this was looking almost 90 degrees. So if this is the rotation of the neutron stars, and this is the side of view, this is this angle yacht. So with all these assumptions, the expression of our signal is going to be f plus t phi h0 1 plus cos yacht squared divided by 2 cosine phi of t plus f cross t phi h0 cos yacht sinus phi of t. Now, regarding the amplitude of the signal, we could put some numbers here. And if we put some numbers here, this can be rewritten as 10 to the minus 27 IZZ So, in the case of a triaxial neutron star, we get that for a typical value of the moment of inertia, let's put at the distance inside our galaxy. If our galaxy center is at 8 kiloparsecs, here I put a 10. Let's say for a gravitational frequency around 100 Hertz, that this could be realistic. And for beautiful values of this equatorial ellipticity, let's say of 10 to the minus 6, one is getting, then the amplitude of the signal would be 10 to the minus 27. Okay, you can make this a bit bigger by just putting this much closer to us, let's say just to 1 kiloparsec. And then the problem is, this will be explained, I guess, in Keith's class, that we really don't know about the values of epsilon, but for normal neutron stars, this will have a maximum value of 10 to the minus 6. For exotic neutron stars, the maximum value can be higher. And for many of the neutron stars that are known, I guess it's around more 10 to the minus 8 to 10 to the minus 9. This might be very small to you, but if we compare with the amplitude of the first gravitational wave detection, the peak amplitude of I0 was 10 to the minus 21. So we are talking a very faint signals. Of course, you would say, okay, you could use another emission mechanism. And if we go to another one that it will be presented in the other class, for example, talking about R mode, rotational modes, in which in this case, the gravitational wave is going to be about 4/3 of the rotational frequency, then the amplitude is going to be more or less something also very small, because this is going to be alpha is a so-known R mode amplitude. This is the value that could start being realistic and optimistic as well. Also going to 100 Hertz, let's put it to a much closer distance. So in both cases, as you can see, we are talking about really faint signals. So these signals are very faint, much fainter than all the ones we have observed so far, but they are long-lasting. In principle, they could last forever. So the methods to search for these continuous gravitational waves are very different, and the problems are very different from the problem of observing compact binary coalescence. Yes? Why I have put that? Well, I guess that this will be explained in the other class. Basically, we are assuming that we have of the order of 10 to the 8 or 10 to the 9 neutron stars in our galaxy, because you can imagine that we are not going to look for these signals outside of our galaxy. Of these, of the order of 3,000 are non-pulsars, and their frequencies, most of them, the great majority of them, are below the LIGO frequency band. So the ground-based detectors only have sensitivity from a few hertz to several kilohertz. And I will show in one of the plots of the later classes, if not Thursday, on Friday, that the vast majority of the non-pulsars are actually below what we could ever detect with the current detectors. There are of the order of 300, well, 200 something, that are in our band. The fastest known pulsar, I think, is around 700 something hertz. And if we are assuming that mechanism will be at twice, spinning, the gravitational wave will be at twice that frequency. So, okay, we search for gravitational waves, continuous gravitational waves up to 2 kilohertz, but basically we don't really expect much sources after 1.5. Many would be at a very low frequency. But also the point is that if you look at those equations, the higher the frequency, the stronger the amplitude. Even if the most majority are at the lower frequencies, the ones that we have more chance to detect are going to be fast spinning and young. So to have also strong deformation, strong spin down, and high frequencies. Maybe these are the fewest, but that's the ones that are going to be the strongest. I'm not sure if that has answered the question. And I guess these properties either will be covered either by Keith or by me. So having talked about the signal, it's time to talk that what the detector records is not just this signal. The data that we record at the detector is going to be a superposition of noise and plus this signal that varies in time and depends on a number of parameters. So it's time to talk about the noise. So here were my amplitude parameters that include the A plus, A cross, initial frequency and polarization, and the Doppler parameters that include sky location, frequency, and all the frequency derivatives. Plus, it could depend on many more parameters if the source, instead of being isolated, is in a binary system, or for example, like in a binary system, accreting matter from a companion. So, noise is something that is going to be random. So we don't know. I cannot predict the noise. But what I can characterize are the noise properties. There are a number of properties that I could talk about the noise. I could talk about the mean, the variance, autocorrelation, or power spectrum. There are a number of properties that this noise could have or not. The first property of the noise that one could have, it could be that the noise could be stationary. And this means that the statistical properties are going to be independent of time. If that's the case, I can talk about ergodic process in which the ergodic theorem is going to tell me that the time averages are going to be equivalent to ensemble averages. If I want to see these fine signals, I will have to integrate, filter the data during weeks, months, or year. These are long-lasting signals. And you can imagine that a detector that is sensitive or has to be sensitive to such a small perturbations of the arms, we are talking like current advanced LIGO is sensitive to displacements of less than 1,000 of a proton, so 10 to the minus 18 meters, 10 to the minus 19 meters. So you can imagine that many perturbations influence this noise. The tides, humans. So the noise clearly is not going to be stationary. It is not the same noise as the detector during the day than during the night. But I'll talk about that in other classes later on. Another property that the noise could have or not is to be Gaussian. So basically I say that the noise is Gaussian if any of my data samples follows a Gaussian distribution. If I consider the noise as a series of data points, a random set, then I'm going to say that the noise is Gaussian if it's governed by the covariance matrix the covariance matrix, I can just write it like this. And the noise of a number of points, I'm going to say that follows a Gaussian distribution. It just follows this thing. X, y minus xy, that's the mean, xj minus mu. For data analysis, we are going to make many assumptions. Most of the theorems we are going to use, we will design like optimal methods under the assumption that the noise is Gaussian and stationary. And the noise is not stationary, and the noise is also not Gaussian. It's full of disturbances. Another property is that the noise could be white. And we say that the noise is white if the signal power is uniformly distributed over frequency. Or, another way to say, is that the data samples are uncorrelated. And we say that the noise is color if the signal does not have equal power in the different bands. Our detector clearly has color noise. One of the other exercises that I guess you will be doing tomorrow is actually going to be to generate Gaussian stationary noise, but color noise following an analytical expression, but of a horrible distribution of, let's say, of advanced LIGO detector, in which our noise basically changes many orders of magnitude across the different frequencies. When we work on data analysis, we could do all the filtering time domain, but actually it's much better to work in the Fourier domain. So in the Fourier domain, I will have to talk about Fourier transforms. A Fourier transform is a linear function that is complex in general, and I can have the Fourier transform and the anti-Fourier transform. And this Fourier transform basically is going to be defined either by all the positives and all the negative frequencies. From here, just one property that I want that you pay attention is that the data that I'm getting from the detector is a real time series. So if x of t is real, then one property that I have to remember is that the Fourier transform of the negative frequencies is nothing else than the complex conjugate of the positive ones. Because all the filtering I'm going to do is going to be in the Fourier domain. It's much cheaper. So let me start explaining now some of the definitions of statistical things. If my noise would be stationary, then all the statistical properties I said are going to be independent of time. Therefore, as I said, time averages are the same as ensemble averages. And if I want to compute, for example, the mean of a certain data, then I can just compute it as basically a time average of my data. If my data is not stationary, that is going to be the case, I can always work not with the infinite amount of data or with 1 year long stretches of data, but I can work with much shorter stretches of data in which each of stretch I can consider itself as stationary. After having defined the mean, I can also define some other quantities that you might know, you're familiar with, like the autocorrelation, an autocorrelation of the time series, that I can compute it as the limit. So basically, if I say that t is the duration of this process, this will be the definition of the autocorrelation. And here I can start warning you that depends on which textbook you look for. There is going to be this part of here, the limit tending to infinity and the 1 over t, that might be there or might not be there. Now, in the case of a stationary random process, it happens that the autocorrelation function does not depend on this t prime. Let me now jump into Parseval's theorem. That basically is going to talk about the energy, or going to tell us that the energy that I can compute in this way is the same if I compute it in time domain or if I compute it in frequency domain. And this quantity here is the energy spectral density of the signal. The total power then I can define like the limit that tends to infinity dt x of t squared, or I can also write it as putting the Fourier transform in this way. In the Fourier domain, that is basically that's I keep. The integral and this quantity here power spectrum or also the power spectral density. The PSD, that is going to be very important for me. Now, this PSD, you can just get that it simply, with this definition, can be written in this way. In where what I denote here, it's simply the Fourier transform between minus t halves and t halves. We will talk a lot about power spectral density, but actually, I'm not going to be using this letter P. I'm going to use, not to confuse you, but the letter S. And people will also call this as power spectral density. Also, this one is what I'm going to refer to the one-sided power spectral density. Why? Well, the why is going to be that since my data is going to be real, anything at negative frequencies is going to be related to the positive ones, and I'm just going to work with the positive frequencies and not them all. This power spectral density is related with the autocorrelation function in the following way.
Hello. So what quantities are this autocorrelation function is relating?
This function is going to be that my power spectral density of the noise, it's a quantity that is going to be extremely important in all my data analysis searches, is basically the Fourier transform of the autocorrelation function. This is the relation of power spectral density and autocorrelation function. If my noise would have been flat, then I would have a flat power spectral density. So then it will be the same, but that is not the case. If I'm talking about a stationary random process, then the Fourier transforms at two different frequencies are going to be independent, statistically independent of each other if I'm considering two different frequencies. And therefore, there is this other property where I mark the complex conjugate. But this is related to the power spectral density of the noise. Since, as I said, I usually like to work with real signals, then if I just want to consider the positive values, many of the integrals that would appear that could go from minus infinity to infinity, I'm just going to integrate from 0 to infinity. I like to define that the relation, this is 1/2, if I don't consider the zero frequency, of the single-sided, double-sided power spectral density, single-sided power spectral density, then this property here, you will see written in the literature that this is 1/2 delta f minus f prime Sx of f. And this is the single-sided power spectral density that basically just differs from the other one by a factor 2. This is a very important property of my data, and in particular of the noise, that will need to be characterized for any data analysis I want to do. So what we'd like is to construct our power spectrum estimators. So this is going to be, the power spectrum is a property of the noise, but it's a property that we have to find. And we will have to find for the data itself. In particular, I'm not going to have an infinite stretch of data. I'm going to have the different science runs of data. So I will have to estimate the power spectrum from a finite duration of the signal. So usually my problem is that I'm going to have one single realization of my data, of my noise, just one single realization of a finite duration. So the first thing, comparing the definition of this quantity, the first estimator that I could come quite easily, or a simplest approach, is that I can construct an estimator, and this is the hat I'm putting on top of the same quantity, the same letter with hat. I design in this way that this is an estimator. I could define it in this way. That is just I'm doing the Fourier transform of a finite stretch of data. And so this is the finite duration Fourier transform of my data. And this estimator of the power spectral density is called a periodogram. Any estimator of a quantity is going to be good. Well, and I also had to think, my data that contains noise is a random variable. So the estimator itself is also a random variable. And as a random variable, I can also characterize properties. So for example, I can compute the mean of this estimator, and the mean of the periodogram of this estimator is very good because exactly is the power spectral density. So in that sense, this estimator is good because this estimator is unbiased. Now the problem is that if I compute the variance of this estimator, then what I'm getting is that the uncertainty in this power spectrum estimate is as large as the measure itself. So yes, the periodogram is unbiased, therefore it peaks at the right quantity, but the variance is huge. If I insist in using this kind of method to estimate the power spectral density, one easy thing that I can do is the so-called, oh, I did not write the name here, that is the Welsh method. That if I have a segment of data of a certain duration, what I can do is that I can cut my data into m segments. I can compute the periodogram, the power spectral density for each segment, and then I can compute the mean of all of them. And if I do that, the variance is going to be reduced by 1 over m, and the standard deviation is going to be reduced by 1 of the square root of m. And this is going to be, after I explain more material, the exercise that you will end up doing tomorrow, that is to use also the first to construct data following the PSD of advanced LIGO curve, and from there deduce or estimate the power spectral density using this Welsh method. Let me also introduce some other quantities and a scalar product. Bala. I stop here. Let me introduce now a scalar product. So, of 2 time series, any 2 time series, I don't care which ones, then I can design the scalar product that you might be seeing in different ways, but this is going to be my notation. In this way, the integral from minus infinity to infinity, this is the Fourier transform, complex conjugate, here, n, I denote the noise in my data. Sn is the one-sided power spectral density, and my g of t and my h of t are my 2 time series. And I do this product in the frequency domain using the Fourier transforms, and the asterisk is the complex conjugate. This is how I like to write the scalar product, but if you start doing data analysis, you will see this scalar product written in many ways. Why? Because in most cases, we are going to be under the assumption that both g of t and h of t to be real, and if it's real, then this quantity here, if you realize, I have, well, first part is that I have this, and this is the complex conjugates of this quantity here. So whatever number plus this complex conjugate is 2 times the real part. So I could just write that this is basically the real part of any of the 2 of them. And given that the real part in the positive frequencies or on the negative frequencies is going to be the same, I can also rewrite this as 4 times the real part of the integral between 0 and infinity and then you might also see many other variations of these expressions, and I just keep it here. Now, going to keep introducing more properties, more statistical properties that you might have studied as undergrads. That is convolution. So the convolution of an input signal, if X is my input signal and basically K is the response of a system, then I can denote the convolution of X with K as the integral can define it in this way. So basically the convolution is symmetric. And what this does, this is impulse response, what it does is basically to spread the signal. Usually a system is going to be a causal system if it only responds after the data somehow has arrived. So usually a causal system is going to be such that K of t is equal of 0 4 times below 0. There is the convolution theorem that basically relates that the convolution, if I do the Fourier transform of the convolution, then this is the same as the product in the Fourier domain. I have not entered into properties of Fourier transforms because I'm pretty sure many of you have studied as undergrads. But basically, the Fourier transform of the Fourier transform is the same. So what this tells me is that if I'm going to do the product of two functions, this is, if I do a Fourier transform of it, then it's the convolution. Convolution and product of functions, they are related. My data that I'm going to be analyzed is not going to be infinitely long. It's going to have two difficulties. First, it's going to be limited in time, and it's going to be discrete. Anything that I imagine that has a limit duration, I could imagine that my data, I can imagine that my signal is of infinite duration, but if I'm just observing for certain time, this is the same. If I multiply an infinite duration signal with a window function of a finite duration. So a signal that is limited duration in time is the equivalent if I would have the product. And if I do Fourier transforms, it will imply that the Fourier transform of my limit duration signal is going to be the convolution. So what is the Fourier transform of a completely monochromatic signal? Do you know what it is? Correct. 1 delta or 2 deltas, depending what we are talking about. Oh, and what is the Fourier transform of the, how you call it, the rectangular box? Yes, excellent. The sinc function. Therefore, the Fourier transform of my beloved monochromatic sinusoidal signal is not going to be the delta function. It's already going, if in case of a discrete data, is going to be a sinc function. just for fun. Next one, correlation. This is more interesting, usually for me. Now, I'm inventing a sign to indicate a correlation between two signals. Minus infinity to infinity, dt prime, xt prime, yt plus t prime. I apologize, I'm already doing very bad letters. So basically, the correlation, what it does, is it going to measure how well two signals match in shape each other, basically when they are relatively shifted. Again, if I relate the correlation in time domain to its Fourier transform, then it's not the product of the signals, almost, but as you see, one has the complex conjugate. And basically, Parseval's theorem that I mentioned half an hour ago is in a special case of the correlation when both x and y are the same and t equals to 0. Okay. Finally, moving into gravitational wave data. What I'm having is that here, what I'm going to be doing is I'm going to record instantaneous estimates of the strain for each moment in time. So what I'm going to have is going to be a digitized series. So for a certain numbers of timestamps, I'm going to be recording my data. LIGO and GEO, I guess you know which detectors they are, so I don't have to describe them. Basically, they are having a sampling rate of about 16 kilohertz. The Europeans, just to make more fun, Virgo, they have a sampling rate of 20,000 hertz. At least both of them use synchronized clocks, synchronized GPS signals. And then this data is recorded in very strange formats that we call frames. And these are files that have GWF ending. Since I have a discretized data, I can start recovering what you know about sampling theorem, because I should know how fine should I be sampling this data in order not to lose information. So, basically, an easy version of the sampling theorem is going to tell me that discretely sampled data with a certain sampling rate can completely represent a continuous signal which only has the frequency content below the Nyquist frequency. And this Nyquist frequency is 1/2 of the sampling rate. If the signal extends above this Nyquist frequency, then it's going to imply that the higher frequencies are going to be aliased down to the lower frequencies, and then our data is going to be messed up. Sometimes I'm going to play with that. And later on, today or tomorrow, I'm going to make use of these kinds of things. But anyway, I'm going to work from now on with discretized data. To make it simpler, I'm going to assume that my data is a non-pathological function of time, that my timestamps that are discrete are going to be equally spaced. So if I have endpoints, and therefore I'm going to have the corresponding discrete functions of the data. That is the measure of this signal at the discretized times. From here, my sampling rate is 1 over delta t. Therefore, F Nyquist that I should be interested to keep in mind, that is 1/2 of the sampling rate is 1 over 2 delta t. I would like to do filtering and many things in the Fourier domain. So now I have to introduce discrete Fourier transforms because I just would have a number of data points. So let me introduce the discrete Fourier transform. So I will now introduce a typical discrete Fourier transform with certain conventions. And on top, they are not going to be the ones that I will be using either some minutes later or tomorrow. Because there are many ways to introduce the discrete Fourier transforms. And then depends what conventions you use, what software you use. You have to be completely aware of all these conventions. We have to start with the F plus and F cross that I was already having sign conventions depending how I define angles or orientations of angles. I've introduced the Fourier transform and I have not even mentioned that there was the plus or the minus sign. Basically, whatever is the Fourier transform, the anti-Fourier has the different sign as you declared before. And when I go to the discrete one, so the discrete Fourier transform, I could just define it -1 and the inverse and then there is this 1n factor needed because delta ij is 1 over n, because what you want is that when you do the Fourier transform of the Fourier transform, you should recover the initial information. Now, with this definition, we would like to know what is the relation between the discrete Fourier transform and the continuous Fourier transform. Basically here, I have a sum. Well, before I was having an integral, but then in the integral there was dt, that I don't have it written here. So the approximate relation is that the continuous Fourier transform evaluated at a certain frequency is going to be similar as delta t to the discrete Fourier transform, where f of k, I just call it k delta f, and this is k 1 over n delta t. If the data is real, then we have that the discrete Fourier transform of the negative frequencies are just the complex conjugates of the positive ones. Now let me start by making remarks or comments. This has been my definition of my discrete Fourier transform. Let me write close to it the continuous Fourier transform. Okay. So if I look at these two expressions, I could say this, I could have written similarly like dt delta t, and then the integral I can convert it into a sum of a certain value, and here a minus I 2 pi f and t. And t would be the corresponding t, and my corresponding t, if I ignore the initial time, I can just write it like j times delta t. Now the discrete Fourier transform, of course I can compute it at any frequency. Now, if I start with n points, n data points, n realizations of my data in time domain, I'm doing this, that is a linear operation. How many independent points can I have in the Fourier domain? If I start with n independent points in time domain, how many independent points can I have in Fourier domain? Lagoda, because I'm, yeah, n what? What did you say? N by 2. So you create information, or by means divided. Well, excellent. So I'm only going to have n independent points. Okay. I've said that I've used a certain sampling rate because I assume that my information, that all the content of my signal is at most between f Nyquist and, of course, minus f Nyquist. 2 times f Nyquist is the band of my data that corresponds to the sampling rate. Okay, and my sampling rate is 1 over delta t. If in this band I'm only going to have n independent values, the smartest things I can do, or the reasonable thing I could do, is to return these data points equally spaced in the Fourier domain. Okay, that means that my frequency space in the Fourier domain is going to be the sampling rate divided by these endpoints. That is sampling rate n delta t. And n times delta t is my total observation time. my Fourier frequencies, then it's simply going to be k times this delta f. So k divided by n delta t. So if I go back here, let's say I'm not going to return at any frequency, I'm just going to return them at my Fourier frequencies. So the f, I'm going to convert just into the fk, that is k time n delta t. This and this vanish, and that is what I have this definition here, with a different normalization. I think I'm getting closer to almost the ending of the class. So basically, what I see is that a natural way to define the Fourier transform would have to be to put the delta t here. More comments. If I do a Fourier transform of the data, no. The discretization in the Fourier domain depends on the total observation time. Of course, if I want to have more resolve finer, my signal in the Fourier domain, of course I can interpolate the data. Or another thing that I can do is to observe longer and longer. There are two things that I can do, either to use more data, to have it more refined in the Fourier domain, or I can just get my data in time domain and add a huge bunch of zeros, and that is what is called zero padding, that many of us use to get much more refined. The time got over, but I'm pretty sure I have already covered my lesson. I could have taught a bit more, but not necessarily, because I can continue where I have stopped tomorrow. So I'm not sure what you prefer, that I stay on time, I guess.
Yeah, that would be better.
Excellent.
Maybe we can take a few questions if there's any.
Louder, because I'm half deaf.
Oh, so because we're taking like the whole of the data which has the signal and the noise.
Yes?
So, and when we are dividing Hello. And when we are dividing the whole of the data into segments, so I was wondering, like, because the whole our detector is like getting signals from continuous sources as well as compact binary sources. So there are two kinds of signals there. So, like this machinery we have done is
not two. You can have many. You can have these transient signals, but don't worry. At the signal-to-noise ratio that we are having now, we are just having a detection 1 every second or third day of these CBCs. Of the continuous, I have been looking for them for the last 20 years and I have not yet seen the first one. So we are still in the limit of low events and low signal-to-noise ratio. Of course, your question makes a lot of sense for different things. In the case that I will be signal-dominated. And signal-dominated is going to be the case for LISA, space mission LISA, and for third-generation detectors. For third-generation detectors like ET or Cosmic Explorer, I'm going to have millions of events a year, thousands of events a day. I'm not going to talk about the CBC waveforms and other things that you have experts in this center, but they are usually what they see most of the days is the coalescence of black holes. These are very short-lasting signals, seconds. If it's neutron stars, minutes. But as soon as the detectors will get more sensitive to lower frequencies, these signals will become long and long in time, 10 minutes, hours maybe. That will be a full, there have been already several summer schools just devoted to that before. The same binary signals for LISA are continuous waves. So all the things that I'm basically explaining here for ground-based detectors, neutron stars, the most easy signal you can imagine. That's going to be the class tomorrow. almost a quasi-monochromatic signal, a sinusoid. I'm not looking for mergers and for this strange, just sinusoids. Just sinusoids that will get complex enough. No problem. Put me as many, not as many, don't put me millions or trillions of sinusoids. But if you put me continued signals, you will put me what? At different frequencies. They don't get mixed together, unless you put me many. If you put me many, that's the case of the foreground for Lisa. Because in Lisa, white dwarf binaries and other things in our galaxy that are in spiraling, they are basically emitting almost monochromatic signals, and we have so many that they produce a background, and you will only be able to detect signals that are stronger. So for Lisa, there is the instrumental noise, and then there is a background noise coming off this foreground because this is signal dominated. So yes, that's a problem.
Okay.
Did I answer the question?
Yeah. Very good. Oh,
But
thank you
on
so
top,
much.
the signals, we have different parameter space, and I can extract things individually. And if not, people can ask me questions over lunch. I'm not very formal.
Okay.